Hello, my name is Junwoo Daniel Park, a current junior at Korea International School, and today I'll be presenting on my study, which matters more for diabetes diagnosis, who you are or where you live. And using a nationally representative data set of nearly 190,000 individuals, this study examines whether diabetes diagnosis is more strongly associated with individual characteristics or with the neighborhood context in which people reside. Here's the table of contents. Now, diabetes represents one of the most chronic diseases of our time, and according to the Global Burden of Disease in 2021, approximately 529 million people were living with diabetes worldwide, a figure projected to exceed 1.3 billion by 2050. And beyond its direct health consequences, diabetes is also closely associated with cardiovascular disease, kidney failure, neuropathy, and premature mortality. It simultaneously imposes substantial economic costs on the healthcare systems and reduces population-level productivity. In South Korea, the trajectory is equally concerning. Diabetes prevalence has been rising not only amongst older adults, but across younger age groups as well, underscoring that this is a population-wide public health challenge rather than one being confined to a specific demographic. Despite this burden, prevention strategies have historically been centered on individual behavior modification alone, such as weight management, smoking cessation, and physical activity. And while these remain important, they don't not fully account for the geographic variation observed in diabetes rates. And this gap directs attention to the role of built environments and whether that environment context in which individuals live in independently shapes the risk of their diagnosis. Now, prior research has established both individuals and environmental predictors of diabetes. Ismail and colleagues identified age, BMI, and socioeconomic status as significant individual level determinants, while Faisa and colleagues demonstrated associations between food environments, walkability at the population level. However, a fundamental limitation persists across this entire body of work. Individual and neighborhood factors have largely been examined in isolation. Studies rarely place both levels of analysis within the same empirical model, making it difficult to assess their relative explanatory weight. My study addresses that gap. Using data from all 250 municipal units across South Korea, we integrate 7 individual level predictors with 8 neighborhood level indicators spanning across healthcare access, food environments, and more into a single binary logistic regression framework. And this allows us to empirically test within the same model and on the same population whether diabetes diagnosis is more strongly explained by individual characteristics or by the municipal environment. And to our knowledge, no prior study in South Korea has undertaken this comparative analysis at the scale. And this leads us to the central research question: is diabetes diagnosis in South Korea more strongly shaped by who individuals are or by where they live? And both sets of predictors are entered simultaneously into the model, allowing for a more direct empirical comparison. The data source that I use is from the 2023 Community Health Survey administered by the National Korea Disease Control and Prevention Agency, with coverage across all 250 Sigungu administrative units. And after excluding observations with missing or invalid responses from the initial approximately 230,000 respondents, the final analytical sample comprises of 188,395 individuals. The dependent variable is a binary indicator of physician-diagnosed diabetes. This analytical model is binary logistic regression, whose general form is shown here on this slide. X sub I denotes individual level characteristics, and Z sub J represents neighborhood level characteristics for municipality. Individual level predictors include age, gender, education, income, BMI, smoking, and walking time. Neighborhood level predictors, all measured at the municipal level, include physician density, population density, transit density, park density, and the density of grocery stores, fast food outlets, convenience stores, and finally, fitness centers. Turning to the results, a brief note on the overall model fit. The Nagel-Kirk R-squared value is 0.159, indicating that the model accounts for approximately 15.9% of the variance in diabetes diagnosis. For a population-level binary outcome across 250 municipalities and across 190,000 respondents, this represents a meaningful, though appropriately modest level of explanatory power. The Cox and Snell R-squared of 0.088 and a -2 log likelihood of 135,000 are consistent with this characterization. Now, examining individual level predictors, the results demonstrate both consistency and magnitude across variables. Smoking carries the largest odds ratio in the model at 1.263, indicating a 26% increase in the odds of diabetes diagnosis relative to non-smokers after controlling all the other variables. BMI follows closely at 1.113, meaning each unit increase in body mass index corresponds to an 11.3% increase in odds, a finding consistent with the well-established relationship between adiposity, insulin resistance, and metabolic dysfunction. Age is also highly significant at 1.052, reflecting the cumulative metabolic risk associated with biological aging. On the protective side, or the negative association side, education has an odds ratio of 0.934, indicating that higher educational attainment is associated with lower risks of diagnosis, likely mediated by health literacy and access to preventive care. Gender is also significant at 0.894, suggesting that women are less likely to report a physician diagnosis of diabetes than men. The most interesting for me personally, however, was income. While technically achieving statistical significance, this carries an odds ratio of exactly 1.0, indicating negligible practical effects. Walking time is not statistically significant at a p-value of 0.197, suggesting that a simple measure of walking duration is insufficient to capture the intensity or the consistency of physical activity. Now, this chart visualizes the odds ratio for each individual level predictor. The blue bars, age, BMI, smoking, and income, sits at or above the 1.0 reference line, indicating positive associations. The red bars, education and gender, fall below it, confirming their protective direction or their negative association. Walking time in gray sits at approximately 1.0, consistent with its non-significant results. The visual distribution reinforces the directional coherence of the individual level findings. Turning to the neighborhood level findings, the contrast with the individual predictors is quite pronounced. Of the 8 municipal level variables, 7 do not achieve statistical significance. Physician density, population density, public transit density, park density, grocery store density, convenience store density, and fast food restaurant density all return p-values ranging from 0.114 to 0.878, with odds ratio effectively equal to 1.0. Once the individual, demographic, socioeconomic, and behavioral factors are held constant, these broad environmental indicators contribute no statistical meaning at all to their additional explanatory power. The sole exception, however, is fitness center density, highlighted at the bottom of the table in red. Its odds ratio is 0.987, so it's statistically significant at a value of 0.007, with a 95% confidence interval of 0.977 to 0.996. And while the effect size is modest, the finding is robust and theoretically coherent. Fitness center density is the one environmental indicator directly linked to opportunities for regular physical activity, a behavior-specific pathway to diabetes prevention, rather than just a general urban characteristic. To summarize the neighborhood findings, 7 of the 8 environmental variables show no meaningful association with diabetes diagnosis once the individual factors were controlled, with fitness centers being the only exception. Now, this pattern suggests that neighborhood level influences aren't absent, but they are very selective, operating through behavior-specific pathways rather than through general characteristics of the municipal environment. Now, drawing together all the full set of findings, individual level factors are the dominant predictors of diabetes diagnosis in this study. Age, BMI, smoking, education, and gender are all statistically significant and substantially meaningful. Neighborhood influences, on the other hand, are very selective. Only fitness center density achieves significance among the 8 environmental variables. This empirical answer to the central research question is that who individuals are carries substantially greater explanatory weight than where they live for diabetes diagnosis in South Korea. Nonetheless, the finding supports an integrated approach, individual risk management as the primary mechanism, complemented by targeted environmental investment where evidence is strongest. Now, these findings carry 4 direct policy implications for diabetes prevention in South Korea. First, individual level interventions must remain the cornerstone of prevention strategy. BMI and smoking are the 2 strongest modifiable risk factors within this model, and any prevention framework that does not prioritize addressing these is inconsistent with the empirical evidence. Second, high-risk subgroups warrant targeted intervention. The regression results identify specific population profiles carrying disproportionate risk, and precision targeted screening is far more resource efficient than broad-based campaigns. Thirdly, public investment in physical activity infrastructure is specifically supported by the evidence. Fitness center density is the only neighborhood level variable to achieve statistical significance, providing a concrete, evidence-based justification for expanding access to community-level physical activity facilities. Fourth and finally, an integrated prevention framework is warranted. Environmental policy should be concentrated on behavior-relevant physical activity infrastructure where the empirical evidence justifies the investment, rather than on broad urban indicators that this model finds non-significant. On to the limitations. The cross-sectional design precludes casual interference between neighborhood exposures and diabetes diagnosis. Municipal level aggregation may obscure within district variation, introducing the risk of ecological fallacy. Additionally, physician-diagnosed diabetes as an outcome conflates the underlying disease prevalence with healthcare access, as individuals with limited access to care may have remained undiagnosed. Future research should employ finer spatial units, longitudinal data to capture how neighborhood change affects diabetes risks over time, and finally, multi-level modeling to formally decompose individual and contextual variants. More refined environmental measures, including walkability indices and green space quality, would also strengthen the neighborhood level analysis. And all of this is what I wish to continue to do in my future research career. Thank you.